In this video, I will show you how to find the partial fraction decomposition for two different fractions. We'll start with a more basic one, and then we'll do a more complicated one after that. So the first partial fraction decomposition we're going to look at is the partial fraction decomposition for 1 over x squared minus 5x plus 6. Now, as you can see, the numerator has a degree that's lower than the degree of the denominator. So we can start out by factoring the denominator. X squared minus 5x plus 6 factors as x minus 2 times x minus 3. So when we see these two factors, we know that we have to decompose the fraction into two smaller fractions. So 1 over x squared minus 5x plus 6 equals a constant a over x minus 2, and then plus a constant b over x minus 3. So what we've done here is we used the third part of the partial fraction decomposition, where we looked at the linear factors of px plus q to power m. Now in our example, we have two linear factors, x minus 3 and x minus 2, and they're both to the first power, so there's only one term for each of these fractions. So what we're going to do now is we're going to multiply both sides of this equation by x minus 2 times x minus 3. So the x minus 2 times x minus 3, that's the denominator of the left-hand side. So if we multiply the left-hand side by x minus 2 times x minus 3, that will simplify to 1, as you can see here. So x minus 2 times x minus 3 times the 1 over x squared minus 5x plus 6 equals a over x minus 2 plus b over x minus 3. Inside parentheses, we're going to have to distribute the x minus 2 times x minus 3. So we multiply the whole right-hand side times x minus 2 times x minus 3. And then we're going to simplify that sum. On the left-hand side, we're just left with 1 because the denominator cancels, and in general, we will end up with whatever is in the numerator on the left-hand side. In this case, our numerator is 1. And then on the right-hand side, we're going to have to distribute the x minus 2 and the x minus 3. And what we'll end up with is a times x minus 3, because the x minus 2 cancels. The x minus 2 in the denominator of a over x minus 2. And for the b, the x minus 3 cancels. So we're left with b times x minus 2. And then we add those two terms. And the equation we have here is what is called the basic equation. Now, this equation is the equation we have to solve to figure out what a and b are. Now, one thing to notice is that this basic equation has to hold for all values of x. So what we're going to do here is we're going to pick some smart values for x that will make our life easier. So one of these choices would be to pick x equals 3, because if we pick x equals 3, then 3 minus 3 zeroes out, and the unknown a disappears, and we just have an equation for b. So b can then be easily found. So we're picking x equals 3 and plug that into our basic equation. So we get 1 equals the value a times 3 minus 3, and then plus b times 3 minus 2. Now if we simplify that, we see that the a disappears, and we're left with just the value of b on the right hand side. In fact, it's b times 1. So our equation becomes 1 equals 1 times b. And that, of course, leads to b equals 1. Then the other value is x equals 2 as a smart value. And when you plug that in, we get 1 equals a times 2 minus 3. And then b times 2 minus 2. So we see that b is going to disappear. And what we're left with then is the equation 1 equals a times negative 1, or 1 equals negative a. And that then leads to that a is equal to negative 1. And all that is left to do then is to plug those two values that we found for a and b into our partial fraction decomposition. So we end up with 1 over x squared minus 5x plus 6 equals a, which equals negative 1 over x minus 2, and then plus our b over x minus 3, and our b was equal to 1. So then we have a 1 there, and that is our final answer. So now let's look at a more complicated example where we have to find the partial fraction decomposition for 9x to the power 4 plus 17x cubed plus 7x squared plus 11x minus 4 all over x to the power 5 plus x to the power 4 minus x minus 1. And the first thing we notice is that the degree of the numerator is less than the degree of the denominator. So that means we do not have to do any long division, and we can start off by factoring the denominator. Now, this is something we did in a previous example. And so once we have the denominator factorized, we can write out what the partial fraction decomposition will look like. So on the left-hand side, we put our fraction, which is 9x to the power 4 plus 17x cubed plus 7x squared plus 11x minus 4 all over x to the power 5 plus x to the power 4 minus x minus 1. So the first factor, or the first term that we need here, is a constant over x minus 1, because we have our first factor is x minus 1. Now, our second factor is x plus 1 squared. So that means we will have two partial fractions with x plus 1 in the denominator. Namely, we'll have x plus 1 to the power 1, and then we'll have an x plus 1 squared. And both of these partial fractions will have a constant in the numerator. So the first constant, we can just call that b, and then the second constant, we'll call that c. And then finally, our final factor of the denominator is x squared plus 1. This is an irreducible quadratic factor. So we write x squared plus 1 in the denominator, and now we'll have a linear term, not just one constant, but a linear term that consists of d times x plus e. And that is our partial fraction decomposition. So we applied the fourth part there, where you have the irreducible quadratic factor in the denominator, and then the numerator is a linear factor, or a linear term. So now what we do is we multiply both sides by x minus 1 times x plus 1 squared times x squared plus 1. And since that is just another way of writing the denominator on the left-hand side, we see that the denominator on the left-hand side will disappear, and we'll end up with 9x to the power 4 plus 17x cubed plus 7x squared plus 11x minus 4 on the left-hand side. And then on the right-hand side, after we simplify some, we get the following expression. Now, pause the video if you need to check the work on this, but this is now our basic equation. And our goal is to plug in some smart values for x. And so, for instance, we see that a smart pick for x would be x equals 1, because that makes certain terms on the right-hand side disappear. So when you plug in 1 on the left-hand side of the equation, you end up with 40. Now, on the right-hand side, we see that every term that has a factor of x minus 1 will completely disappear. That will make everything 0. So the only thing that we're left with are the factors that belong to a. So we're going to plug in our smart value of 1 into x plus 1 squared, and then x squared plus 1. So when we do that, we get the 1 plus 1 squared, and then we get 1 squared plus 1. So that first factor is 2 squared. That gives us 4. And the next factor is 2, 1 plus 1. And so we have 8a equals 40. And then we get a equals 5. Now, the next smart value would be x equals negative 1. Because every term now that has a factor of x plus 1 will disappear. Now, on the left-hand side, if you plug in negative 1, you get negative 16. And on the right-hand side, we see that the only term that doesn't have an x plus 1 in it is the term with the factor or the coefficient c. So we're going to have c times negative 1 minus 1, and then multiplied by negative 1 squared plus 1. And when we plug that in, we see negative 1 minus negative 1. That gives us 2. And then negative 1 squared is positive 1. So we get 1 plus 1. That's 2. So we have negative 2 times 2, or together that gives us negative 4c. And then when you solve that for c, you will find that C equals 4. At this point, we're kind of out of the really smart values that cancel out several coefficients at the same time, but a good value to pick is still x equals 0. And then since there are 5 coefficients, we need 2 more values for x, and that is pretty random. But since we picked 0, 1, and -1, we could maybe pick x equals 2 and x equals -2. And so I'm going to fast forward now where I plug in these values and then get some equations for the fact or the coefficients that we are missing, b, d, and e. So what you see here is that you end up with 3 equations in 3 unknowns, the unknowns being b, d, and e. And from college algebra, I hope that you remember that 3 equations in 3 unknowns typically have a unique solution. And this is not something that I would put on a test where you have to solve a system of 3 equations in 3 unknowns. What I'll try to do is I'll try to set up the problem so that you can pick some smart choices for x that avoid you having to solve a system of equations. So this problem was really there for an illustration where you see all the different types of partial fraction decompositions in one problem. So once we have those 5 values for the coefficients, all we have to do is to plug in those values into the partial fractions. And that will give us a final answer that looks as follows.